The learning objective for this video is to learn how to represent our chemical reactions using chemical equations. Chemical reactions are chemical changes that occur. Chemical changes involve changes in what compounds are present in the substance. And so we have several observable changes that may indicate a chemical change has occurred. That could be a color change, such as when the leaves change color in the fall. It could be emission of light, such as glow sticks. It could be emission or absorption of heat. Formation of a gas, such as when you bake bread or other baked goods. Or formation of a solid. These are all evidence that chemical changes occurred, but just because you see one of those things changing does not necessarily mean it is a chemical change. Physical changes can also involve you seeing gas forming or solid forming because those are phase changes. Phase changes are physical changes. So when you boil water, for instance, you'll see steam, and that steam contains water molecules. But the water down below also contained water molecules. That is a physical change from a liquid into a gas. But it's still H2O. It still has 2 hydrogens and 1 oxygen. So that's a physical change. We can also represent physical changes using chemical equations as shown here, and the difference is within the phase symbol, not the chemical formula. So our chemical equations help represent what did we start with and what did we end with. And so what you start with is called the reactants, and that's always on the left-hand side. Now, it doesn't matter whether you put the water first or the sodium hydrogen carbonate first. You could put either one first. That doesn't matter. What matters is that it's always on the left side of this arrow. This arrow separates what the compounds we started with, the reactants, from the products. And again, these products could be written in any order. I could put the carbon dioxide first, I could put the water first, that doesn't matter. What matters is that all of the products are on the right side of the arrow. We also have these phase symbols to help represent the state of matter that each of these substances is in. And so, for instance, if I put sodium hydrogen carbonate solid here into water, it could change into this. And so these phase symbols actually represent the phases that are present. So those states of matter are shown here. So for instance, we have 2 aqueous solutions here. You can't see what's dissolved in them, but this first solution contains potassium and iodine ions, and the second solution contains lead and nitrate ions. When the 2 solutions are mixed, there still are some ions in solution, but there's also a solid down at the bottom of the container. And so when we represent this reaction using our chemical symbolism, this first is represented by potassium iodide aqueous, meaning it's dissolved in solution. This is lead and nitrate, so it's lead nitrate dissolved in solution. And then this solid down here represents the solid, and these aqueous things are the potassium and nitrate. So if you have pure elements in your chemical equation, there are states of matter at room temperature that you should be aware of so that you can accurately represent their state of matter for those elements. So this is for pure elements, not compounds. Most of the elements naturally exist as solids. There's only 2 elements that naturally occur as liquids at room temperature, and that's bromine and mercury. Gallium's melting point is slightly above room temperature, so it could be a liquid on really warm days. But we'll consider it a solid. Then there's gases. The gases are the non-metal elements. And so, for instance, nitrogen and all of the noble gases, those are the gases, and hydrogen too. So it's easy to remember which ones are gases, which ones are liquids, and then the rest are solids. So this works for any of the pure elements that in their neutral form. So if you see a charge on it, it's an ion, not a neutral molecule or neutral atom. So pure phosphorus, it would be a solid. Iron would be a solid. Oxygen would be a gas, and bromine would be a liquid. These two are diatomic elements, and the phosphorus is a polyatomic element. You might recall our diatomic 7, all of nitrogen through, that makes it number 7 shape, and those are our diatomic 7. So put 2 A's in diatomic. So those are our diatomic elements, and so most of our diatomic elements are gases, except for bromine and iodine. Bromine's a liquid and iodine's a solid. So our chemical equations are, we separate our reactants and our products using an arrow. Most of the time you'll just see a regular arrow, but there's other things that you might see besides just that arrow. You might see what's this left-right harpoons. These are single-sided arrows. They go both directions. This represents that the reaction actually goes both in the forward direction and in the backwards direction. So both reaction directions are happening. This is what's known as equilibrium. But we won't go into equilibrium much this semester. So if you see this double-ended arrow, there's times when you'll use it, but most of the time you're not going to be held accountable for actually using the double-ended arrow. If you're ever in doubt, just use the single arrow. Then you might also see things written over the arrow. Things written over the arrow are catalysts or things that were added to the reaction to help it go. This little delta symbol would mean heat, and if we saw MnO2 over a reaction arrow, that could mean that MnO2 is a catalyst for that reaction. Catalysts are not reactants because they are not consumed in the chemical reaction. They're just added to help make things go faster. Additionally, chemical reactions need to represent the changes that have occurred. So this chemical reaction shows the combustion of methane. And so it says CH4 plus O2 equals CO2 and H2O. This tells us that when we burn methane with oxygen, we produce carbon dioxide and water. But there's a problem with how this is written right now. Do you see it? The problem is that we have one carbon here, but we have 4 hydrogens and only 2 hydrogens on that side. Additionally, this has 2 oxygens and this side has 1, 2, 3 oxygens total. And so the amount of hydrogens and oxygens is not the same on both sides of the equations. We cannot transform hydrogens into an oxygen. That's not possible. And so we can't have a chemical equation that describes something that's impossible. We need to balance our chemical equations. And we balance chemical equations by putting coefficients up in front to show what ratio these compounds react in. And so these are going to react. For every 1 methane, I'm going to need 2 oxygen molecules. This 2 comes up in front to represent that we have 2 separate O2 molecules. We don't have 1 O4 molecule, we have 2 O2 molecules. Additionally, we form 2 water molecules. We don't form 1 H4O2 molecule. These are each a water molecule. So we need to say that we'll make 2 water molecules. Changing subscripts changes the chemical formula of the compound. That changes the chemical identity of the compound, and we don't want to do that. So we need to just add these coefficients up in front. And so now our reaction is balanced. It takes some practice learning how to balance chemical equations, but there is a strategy to it. I always like to start off with whatever looks the most complicated, has the most subscripts happening, and then I try to balance out the other things, leaving pure elements for the end. A lot of times you're also asked to figure out the chemical formulas, and it's really essential that you get your chemical formulas correct before you attempt any balancing. Because if you are having a hard time balancing, then it might be because you got a chemical formula incorrect. If you end up with an odd number of something on one side and an even number on another, then you might be best off just doubling everything so that you have even numbers everywhere. We always report our coefficients as the lowest whole number ratio. So if all of your coefficients end up even, then you're going to need to divide by 2 to simplify. And then you got to add your phase symbols on there. If you are translating a description of reaction into symbols, then you can, here's some tips for translating those words into symbols. Some of these words are trying to clue you into what's reacting, and others are trying to clue you into the state of matter. So if you see something saying it's burned in air or reacts with air, it's reacting with oxygen gas in the air. Oxygen gas is a diatomic gas, and that's the most reactive component of air. If you see blah 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 metal, like iron, metal, then that's referring to the pure element. And all of the metals are solids. And so that's telling you the state of matter, except for mercury. Mercury would be a liquid. If it says like hydrochloric acid, acids are always going to be aqueous. So that's telling us our state of matter. If it says is combusted or burned or combustion of, that's kind of like burning with air. And so that's saying it's reacting with O2. And compounds, we'll go into combustion reactions a little bit later, but combustion reactions involve reacting things with O2, and if it contains only carbon, hydrogen, oxygen, like our hydrocarbons would, then the products are always carbon dioxide and water. If it says elemental hydrogen, elemental nitrogen, elemental anything, then that's telling us about our diatomic elements that we have to recognize, and then also the respective state of matter of each of those. And so all of these are gases, that's a liquid, and that's a solid. So let's practice balancing our chemical equations. This did not format correctly. These are lines I tried to insert to give me room to balance. I don't know why it's displaying as arrows. That's weird. So if I look at this first one, I have Fe2O3 on my reactant side. That tells me I have 2 irons and 3 oxygens. On the product side, I currently have 1 iron and 2 oxygens. And so if I look at my oxygen count here and my oxygen count here, I have 2 and 3. And so I got to make these equal somehow. And so I can think about what's the lowest common multiple between my 3 and my 2. I'm trying to make kind of a table to show what I have on each side of the equation. So to make 3 and 2 equal on both sides, I can bring both up to 6. And so I can try to bring both oxygen counts up to 6 by putting a 2 in front there and a 3 in front here. And so 3 times 2 is 6. 2 times 3 is 6. Then for iron, I have 2 times 2, which is 4. And so I'm going to need 4 over here in order to balance that out. So now we have our balanced chemical equation for the first one. Now for the second one, it's showing that I have 4 phosphoruses reacting with sodium hydroxide and water to produce, that's pH3. Gotta give myself a line again. And then sodium hydrogen phosphite. So I have to balance this out. I can see that phosphorus is in 2 different compounds and hydrogen is in 2 different compounds. And so that's going to make the hydrogens really difficult to balance and the phosphorus more difficult to balance. And then here I have oxygen in 2 different compounds. And so again, that's going to make oxygen get difficult to balance. And so sodium appears in only 1 compound on each side. And so I'm going to start by balancing out my sodiums. And so I'm going to put a 2 here. Now let's count up my hydrogens and oxygens. So when I put a 2 in front here, let's go ahead and kind of make out a table to help us keep track of everything. So I know I got 2 and 2. And so now I have 2 times 1. I'm going to count my oxygens. So I have 2 oxygens here, 1 oxygen there, so that's 3 oxygens. On this side I have 3 oxygens. Okay, cool, that's balanced. All right, now let's count up the hydrogens. I got 2 times 2, which is 2, plus 2, and so that's 4. And now I have 1, 2, 3, 4 hydrogens. Okay, great. All of the sodiums, oxygens, and hydrogens are balanced. Now I got to think about the phosphoruses. On this side I have 4, and on this side I only have 2. And so that's going to be a problem. But I got to maintain the same proportion of sodium, oxygen, and hydrogen because those were already balanced. So one thing I can do is double everything for these compounds. And let's see if that fixes everything. And so instead of putting a 2 there, I'm going to put a 4 and then double each of these. Now let's count up how many of each thing I have. I got 4 sodiums on this side. 2 times 2 is 4. Now I got 4 oxygens plus 2 more oxygens, that's 6. And that's 2 times 3, which is also 6. Now I got 4 hydrogens and 8 hydrogens. 4 plus 4 is 8. There we go. And that's 6 plus 2 more, and so that's 8. And so now I got 2 times 1, and so that's 2 plus 2, that's 4 phosphoruses, and that's 4 phosphoruses. So I'm balanced now. Here's another practice problem. This one reads, liquid hexane is burned in oxygen gas to produce carbon dioxide and water vapor. And so I got to translate these words into a skeletal chemical equation. And so it says liquid hexane. And so I know that hexane is going to have 6 carbons. And since it's going to follow my 2n plus 2 rule, that's going to be 12 plus 2, which is 14. And so hexane must have 6 carbons and 14 hydrogens. Oxygen is one of our diatomic elements. Gotta put in my face symbol so I don't forget. And then it says to produce, and so that's an arrow. Gaseous carbon dioxide. Following my nomenclature rules, that means 1 carbon and 2 oxygens. And then water is H2O. Vapor means gas. And so if I start with, let me go ahead and put in what I know so far. Alright, so to start balancing this, I always, for combustion reactions, I always start on the left and balance out the carbons and the hydrogens and then come back to the oxygens. Oxygen's a pure element here, and since it exists in two different compounds over here, I'm going to save oxygen for the last bit. So I'm going to put a 6 here so that I have 6 carbons on both sides. Then I'm going to have, that says 14 hydrogens, and so I got to put a 7 here. And so then I got to count up my oxygens. I got 7 oxygens from that compound, and then I got 6 times 2, which is 12, which is 19. And so I got 19 oxygens. And then I got to come over here, and I got to put like if I put 19, that's going to be 19 times 2. So like 19 halves. 19 halves work? I can't have half of a molecule though. And so instead of having 19 halves here, that's like really weird. I'm going to instead multiply everything by 2 so that I have an even number of oxygens on this side. Instead of having 19, I'm going to have 38 oxygens. And half of 38 is 19. And so that will give me an even number of oxygens to work with. So I'm not stuck with weird half molecules. Yeah, it's supposed to be 14 H2O. Alright, here's a practice problem for you. Go ahead and pause the video and unpause the video when you are ready to check your work. Okay, let's go over this. So on this side of the equation, I see 4 phosphoruses. And so I'm going to go ahead and put a 4. Let me rewrite this so that I have room to write the coefficients in. If you want to remember to put your coefficients in, you can leave yourself blanks when writing it. But if by convention, we don't write ones. So don't put ones unless you're instructed to. Like if you're doing an online assignment, you might need to put ones. Otherwise, ones are implied. But I'll put a 4 here. 4 times 3 is 12. And 6 times 2 is 12. And so now that should be balanced. On this side, I'm going to need, let's see, it says Al2, Fe2O3. The oxygens are already balanced. It's really just the iron and the aluminum that need balanced. I'm going to need 2 aluminums over here and then 2 irons over here to balance out my equation. For ionic equations that involve polyatomic ions, I like to think of the polyatomic ion as one group. So instead of thinking of individual phosphoruses and oxygens, I recognize that this is phosphate. And so I think of this as one phosphate. On this side, I have 2 phosphates. And so I'm going to need a coefficient of 2 in front of this in order to give me 2 phosphates. That's going to mess up my sodium count, so I'll do sodium next. 2 times 3 is 6, and so that's going to give me a 6 on the product side. And so I got to have 6 sodiums, and now I got 6 chlorines, and so I got to come back over to the reactant side and give myself 6 chlorines. So 3 times 2 is 6. That gives me 3 magnesiums. And then on the product side, I have 3 magnesiums. And so I'm done there. For this next one, we have to translate a word problem into chemical symbols. And so it says when aluminum metal, and so that's telling me Al solid, reacts with oxygen gas in the air, oxygen is diatomic, it produces a white powdery compound, aluminum oxide. So this is an ionic compound. Since that's an ionic compound, it's going to be made out of ions of aluminum and oxygen. Aluminum has a common ion charge of 3+, and oxygen has a common ion charge of 2-. And so aluminum oxide, to write a neutral ionic compound for aluminum oxide, that is Al2O3. And since it describes it as a powdery substance, that's describing a solid. So if I put this into my chemical equation, then I can balance it. Alright, so this has 3 oxygens, that has 2, so I'm going to need to bring this up to 6 in order to have the same number on both sides. So now I did that because I wanted to have, I had an odd number on one side and an even number on the other, and so I was trying to make it even, and I could do that by doing a 2 and a 3, and that's going to make that coefficient a 4. That concludes our video on balancing chemical equations.